Hey everybody, today we're going to talk about single displacement reactions, and another word for displacement could be replacement, because this is going to be a type of reaction where one element replaces a different element in the reaction. So a few things you should have out in order to get ready for this lesson. Number one, grab yourself a periodic table, and you can see that I have my diatomics highlighted just in case we need to use those down the road. Those are those 7 elements that always pair up with a similar type of element. You also want to have out your whole year resources page and flip to the second page, and we are going to be looking at this thing today, this thing called the activity series. So if you don't have those, pause the video, grab those, and then continue. So you'll notice on the note guide, there is this really weird looking kind of equation. It says that A plus BX yields AX plus B. So what does that mean? Well, I'm going to kind of take this another direction, and we're going to pretend that we are at the school dance. And you're going to have to excuse me for a second. I'm using some gender stereotypes, if you will. I'm putting a guy with a girl in this happy couple over here. But if you want to substitute in any other genders, obviously feel free. But just for the sake of this example, we have our blue guy over here, and we have a couple made with our red guy right here, and our green girl right here, as denoted by her long hair. So, turns out the guy in blue has a theme song, and I'm going to play the beginning of the theme song for you now. So this is this guy's theme song. Yes, indeed. So Mr. Blue Guy is also known as Mr. Steal Your Girl. And unfortunately for our man in red, here's what's going to happen. Mr. Blue Man is going to come in. He is going to kick Mr. Red Man to the curb. Mr. Red Man's going to be off by his lonesome, and the green girl ends up with the blue guy. So what do we get? Well, we get this, right? So this is how this reaction works. We have something that's by itself. That was our blue man. Remember over here, Mr. Blue Man. He comes in, and he is going to knock out part of this couple, also known as a compound. So we're going to see a compound in these chemical reactions. And part of that compound is going to go away, and Blue Man is going to join the other half of that compound, in this case the green girl, and the part of the compound that was kicked out is now going to be by itself. So that's this red guy over here. So let's see that in action in our chemical reactions. We have a few different examples on the bottom. I'm going to save this letter C for the end, so we will go here, but we're just going to take a second before we do. So let's start here. Let's start with this copper reaction reacting with hydrochloric acid. And so there are some things that we need to ask ourselves. Number one, copper by itself. If you look at copper on the periodic table, you're going to notice that copper can have more than one charge, right? It can be cuprous, it can be cupric. And so we need to figure out which one of those it is. And if it's by itself, there's no way to figure that out. So it turns out we actually need to tell you the charge of a transition metal by itself. So that's why we put this example on here, just to let you know that if you encounter this on homework problems or on a test or something, we need to tell you the charge. And so I'm going to do this. Let's make this copper the cupric version. I want to make this copper the +2 version. So again, we'd have to tell you what the transition metal's charge is. And so you actually have two options. What if copper came in and replaced hydrogen? We'll do that in pink. What if copper came in and replaced chlorine? We'll do that in blue. So we could put Cu replacing H, and if we did that, we would get Cu with Cl, and then H would be off by itself, so we'd get H. Or in blue, we could get Cu replacing Cl to end up with H, and then we could get Cl by itself. And so the question is, which one of those is correct? Which one of those works best? And to answer that question, we need to think of charges, right? So let's look at HCl. We know that chlorine always has a -1 charge, which means that hydrogen in this case is behaving as a +1 charge, right, to cancel out that chlorine and make us have a neutral compound. Which means, if we go back to the guy-girl example, this copper, when it comes in, can't really end up with hydrogen, right? If it ends up with hydrogen and comes over here to make CuH, if it ends up with H, then you're going to have a situation where you have two positives together and positives repel one another. So we can't have that, right? We can't have Cu with H because they're both positive. So when copper comes in here, it needs to end up with chlorine. So if it's going to end up with chlorine, it needs to kick out hydrogen, which means we basically want the pink reaction. So I'm going to go ahead and I'm going to erase all of this blue stuff. That's not what we want. But you're going to notice something else. We've put Cu, which is a +2 charge, with Cl, which is a -1 charge. So if you have a +2 and a -1, you have to cross those charges correctly, right? So you have a Cu +2, Cl -1. They're going to be 2 chlorines for every 1 copper. And similarly, hydrogen, on your periodic table, perhaps you've identified the 7 diatomics. Hydrogen is one of those 7 diatomics, one of the Brinkelhoffs, so it always gets a subscript 2 next to it if it's by itself, which it is in this case. Remember, in HCl, it's not by itself, so it doesn't get the 2 next to it. Now, we're going to balance this, but we're going to balance at the very end. We're going to balance everything all together. So let's continue predicting our products. Looking at number 2. Again, we have 2 options, right? Let's think of the compounds we could make. We could put, at the end of the day, Cl with Br, or we could put Cl with Na, right? And how do you know which one to do? Well, you look at their charges. So Cl is a -1, Na is a +1, and Br is a -1. So what is Cl going to end up with? Well, Cl is going to have to end up with Na, because if it doesn't end up with Na, if it ends up with Br, we'd have 2 -1s together, and that's not good. So let's get rid of that option. Excuse me. My eraser broke. Let me jump back in here. Let's get rid of that option. We're also going to get rid of this ClNa option because with the ClNa option, it's written backwards, right? You always want to have your cation written first. So really, when these two come together, we want to have Na end up with Cl. They do that in a 1-to-1 ratio because you have a +1 and you have a -1. And then what's left when you do that? Well, what's left is the bromine that got kind of kicked to the curb. And so we're also going to have bromine. And you'll notice I'm leaving space to balance here. But bromine is one of those diatomics, so it's really Br2. Coming down to number 3. Number 3 is a little bit weird because here's what we would expect. We expect Na to be a +1. We expect OH to be a +1. We expect O to be a -2. And so when we put those together, we want the positive with negative, so you would expect that we would have Na2O, when you cross the charges, plus H2. And that's very logical. Totally understand why you did that. But here's the problem. It turns out that water doesn't divide that way. Water actually has a polyatomic ion hidden within it. Water is actually HOH, which is hydroxide. So you'll recognize the OH as hydroxide, which means, let me change the color on that, which means this. The OH part of this is a -1, and the H part of this is a +1. So when these come together, they actually make the following. They actually put Na with OH, and those are +1 and -1, so it's simply NaOH. And then H goes off by itself, but it gets a 2 because it's a diatomic. So really it's NaOH plus H2. So be careful when you split water. It splits into H and hydroxide, not H and O. All right, looking at number 4, we again have a transition metal. Again, I need to tell you the charge. So we are going to make this ferric. We're going to make this +3. Now for this copper, you might ask, well, what's the charge? But you can figure that out because you know that sulfate is a -2 charge. So that means if we have a neutral compound, copper here has to be a +2 charge. So when we make our products, iron has to end up with sulfate. We have a +3 and a -2. So we're going to end up with Fe2SO4 3. And then we get copper by itself. And a lot of people want to put like a +2 here. You don't need to do that. In fact, you shouldn't do that because when this thing is by itself, we're not going to treat it as an ion. We're not going to say that it's gained or lost electrons. So don't worry about that it's a +2. It is a +2. We've identified that over here, but that doesn't matter to us on the right-hand side. It's simply copper by its lonesome. Finally, number 5, a lot of stuff going on. So zinc, that is in the middle of the periodic table, but zinc is one of those ones that's always a +2. Hydrogen, remember, is part of water here. Water splits into H and OH. So OH is -1, H is +1. That means zinc is going to end up with hydroxide. So when we complete this thing, we are going to get Zn OH2 plus hydrogens by itself. Okay, so don't end the video. We're not done yet. We have predicted all of these single replacement reactions. You'll notice they all look very similar. We have something by itself. We have a compound. We end up with a new compound and a new thing by itself. But what if the following happened? What if we had our situation with Mr. Steal Your Girl and it looked more like this? What if Mr. Steal Your Girl here in blue came in to steal the girl, do what he does best? But Mr. Redman says, I don't think so. I'm going to put up the old stiff arm here, and you are not getting past my stiff arm. That's a really big hand. But regardless, Mr. Blue Guy cannot come in and break up this relationship. And it turns out sometimes that happens in these reactions. So really, again, we're kind of making some really bad gender stereotypes here, but let's do this based on strength. So if the blue guy is really, really strong, and the red guy is really, really weak, then this can happen, right? The girl can be stolen, we'll end up with the unhappy red guy, blue guy comes in, gets the girl regardless. What if, though, the situation is reversed? What if the guy trying to steal the girl is really, really weak? And again, I know this is a terrible stereotype, but it works for the analogy, so we're just kind of going with it. And what if the red guy is really, really strong? And hopefully, again, we're talking more about emotional strength than physical strength here, but regardless. If the red guy is really, really strong, he's going to put up the stiff arm, and Mr. Blue Man can't get by, can't steal the girl. So we would say, we would put an X over this yield sign, and we would say nothing happens, or NR. NR means no reaction. So how do we know if that's going to happen in the chemical world? Well, that's why we have this thing called the activity series. The activity series is essentially a list. And as you go higher on the list, so closer up towards lithium at the top here, see lithium's at the top, this is the strongest metal on the list. So as you go higher towards the top, it's the strongest thing. So let's look at our examples and let's figure out where they are in the activity series and which one is strong enough to do the replacing. So have this activity series out. I'm going to reference this activity series, but we're going to work through the examples that we've just tried together. So in number 1, copper and hydrochloric acid. Find the two things that are replacing one another. So you'll notice the two things that are doing the replacing. Copper is trying to replace hydrogen. So in order for that to happen, copper needs to be stronger than hydrogen, or copper needs to be higher on the list than hydrogen. So is copper higher on the list than hydrogen? Well, it's not. If you look at those two, hydrogen is down near the bottom. They're in the second box from the bottom. Hydrogen is actually above copper. So hydrogen is going to throw out the old stiff arm, and we are going to see no reaction for number 1. And if there's no reaction, you don't have to balance. So the reason that I didn't balance any of these is because any that are no reaction, we're not going to balance. Our job is done. Number 1 simply does not react. And some of you who are clever might ask yourself, well, wait a second, do I really need to do the reaction prediction if I know they don't react? And the answer is no. So really, I've done this in a backwards order just to kind of step us through it. But if you want to look at your activity series before you do this prediction, that might be really useful because if it doesn't react, your job is done. You don't need to do anything else. Let's look at number 2. And you have to be careful with number 2 because a lot of us are going to try to find sodium on the activity series, but sodium's not the thing doing the replacing. What's happening here is that chlorine is trying to replace bromine. And it turns out that the activity series for anions, you'll notice those are both negative. The activity series for anions is over here where it says halogens, because we're really only going to use the halogens. So now we're looking at chlorine and bromine. You'll notice that chlorine is above bromine, And so if chlorine is above bromine, this can happen. Chlorine is able to go replace bromine. So we can't write no reaction. The way that we finish this off, if it can happen, is we balance. So I'm going to draw the list once, just so we can all be on the same page with balancing. Reminder, when you draw the list, you put down everything that's in the reaction. So we have Br, actually let me keep these in order. We have Cl, 2 on the left, 1 on the right. We have Na, 1 on the left, 1 on the right. We have Br, 1 on the left, 2 on the right. So we need to fix those. How can we do it? Well, if we need 2 Cl's on the right-hand side, we're going to put a coefficient of 2 here. Change that to 2, but it also changed the NAs, so we got to put a 2 there. That's good for chlorine, but we've changed the sodiums. 2 on the right, let's get 2 on the left by putting a 2 there. That changes that to 2, so sodium's good, but it also changed Br. Br is now also 2, and all is well. Again, you can leave those coefficient lines in front of Cl2 and Br2 empty. That means that they have 1 of each. Okay, jumping down to sodium and water. So we need to look at what's replacing what. Well, sodium is trying to replace H2O. I'm sorry, trying to replace H in H2O. And so can sodium replace hydrogen? If you find the 2 on your list, you're going to notice that sodium is well above hydrogen. So yes, sodium can replace hydrogen. That means that yes, our reaction can occur. And now our job is to balance. Let's again make our list. There's a nifty little trick here that we're going to use. So on the left-hand side, we have NAs, 1 on the left, 1 on the right. On the left-hand side, there are H's, but I'm actually going to look at this version of water, this HOH version. So I'm going to say there's 1 H on the left-hand side. I'm looking at just the green H. And on the right-hand side, I'm just going to look at the H2. I'm going to say there are 2 H's. And the reason that I did that is I'm going to leave OH as a polyatomic ion. So on the left, there's 1 blue OH. On the right, there's 1 red OH. And that is coming from our NaOH right here. And so when we do that, you'll notice that the only thing that has a problem is hydrogens. 2 on the right, 1 on the left. So in order to fix that, we need to put a 2 in front of H2O, which really we're looking at this version of H2O. So that gives us 2 H's on the left. It also gives us 2 OH's on the left. So now we've successfully fixed our H's, but our OH's now have a problem. So now we have 2 OH's on the left. We got to get 2 on the right. How can we do that? We got to put a 2 here. That changes our OH's to 2, but it also changes our sodiums to 2. So we've successfully changed our OH's, but we've messed up our sodiums. So how can we finally fix it? Let's come through. Let's put a 2 in front of sodium here. That makes 2 sodiums on the left-hand side as well. Everyone's happy. Everyone is done. Looking at number 4, we have iron. We have iron and copper. Find them on your activity series. If you find iron and you find copper, you will notice that iron, Fe, is well above copper. So iron can replace copper. This can happen. We need to balance. And when we balance, again, let's make our list. We have Fe's on both sides. We have 1 Fe on the left. We have 2 on the right. We have coppers on both sides. We have 1 on the left. We have 1 on the right. And I'm going to keep SO4 as a group. I'm going to say that I have 1 SO4 polyatomic ion on the left, and I have 3 of them, 3 of those units on the right. So as a reminder, notice that Fe has a discrepancy here. We have 2 on the left, 1 on the right, but we want to save Fe for last. Why is that? Because Fe is by itself. So anything by itself, let's save that for last. And so really the thing that we want to change first is SO4, right? SO4 is in a compound on both sides. So if it's on a compound on both sides, let's do that first. In order to balance SO4, we need to put a coefficient of 3 in front of copper 2 sulfate. That'll give us 3 sulfates on the left. It'll also give us 3 coppers on the left. So we've fixed sulfate, but we have a problem with iron and copper. They're both by themselves, so we should save them both for last, but they're both similar, right? So let's fix copper first as we go up the list. If we put a 3 here, that gives me 3 coppers on the right. That's good. And then if I want to fix iron, I need to put a 2 here. That gives me 2 irons on the left. That is good as well. All right, finally, number 5. Let's look at our activity series. Look for zinc. Zinc is attempting to replace hydrogen. Can zinc replace hydrogen? Well, zinc is above hydrogen on the activity series. But there's another little phrase written on your activity series, right? So zinc is all the way up here, hydrogen is up here. But in zinc's box, there are some words. They say, react with steam, but not cold H2O. So steam would be like 100 degrees Celsius and above. Cold H2O would be, lower than that considerably. So if we look at what we have 0 degree water. 0 degree water is the freezing point of water. So we have water that's as cold as it gets before it can freeze solid. This is definitely cold water. So if it's cold water, based on our activity series, zinc cannot react with that. Zinc can react with steam, but not cold water. So we're going to put an X over this, and we are going to say no reaction. As you'll notice, as we start to get going with this, there's a lot of practice that happens, right? We need to know how to do our chemical reactions. We need to know how to predict them. We also need to know how to balance. We need to know how to name. We need to know how to write formulas. We also need to be able to employ the activity series when necessary. So all of that is to say, getting a lot of practice with these sorts of things is really a good idea.